Greetings, Math 141. Welcome to episode 3 of Recitation this summer. As always, I'm your host, Bailey. Today, we are going to be introducing the notion of limits, which is very exciting. This is a huge step in your journey through calculus. And in particular, we note that you can't spell limit without lit. That's what I like to say. I don't know. I'm sure you'll be saying it by the end of this video if you don't already feel that way. In particular, the two sections which we're going to cover some problems from are section 2.1, rates of change in tangent to curves, and 2.2, limit of a function and limit laws. Just like you and I, limits are required to follow laws. They aren't allowed to act all crazy and anarchica, I don't know. But they need to follow laws, which makes them nice and easy to work with. So without further ado, let us jump in and do some problems. First problem I would like to do today is problem 4 off of this homework. And this asks, it has two parts. We're just going to do the first part here because once you do the first part, the second part is not so bad, mostly just plugging stuff into a formula. So here we are going to find the slope of the curve. So the curve is y equals 3 minus 4x squared. And the point, so at the point, let's see, they call it P, and it is -4, -61. All right, find the slope of the curve. So this is one of those new things which we introduced in this section. We've seen slopes before in the past, but we've only ever seen slopes before with lines, right? A line, we can calculate the slope nice and easy. It's just rise over run, right? So M is change in y over change in x, or in particular, if I have, say, the point x1, y1, and I've got this other point x2, y2 on the line, I can calculate the slope by y2 minus y1, that's my change in y, over change in x, which is x2 minus x1. And if you prefer, you can do y1 minus y2 over x1 minus x2. It makes no difference. But this is something we've seen before, right? We're comfortable with calculating the slope of a line. But now we're asking the slope of something which isn't a line. This, in fact, is a parabola. We can see that because I've got this square here. So this is where things are new. However, we're going to do it in a very similar way. So what we want, we will look at the point. So here we can kind of think of P as, if we want, we can think of this as x1, y1, right? This is just some point on the curve where x1 is -4, y1 is -61. And so we're going to look at the point -4 plus h, and then we're going to plug h into our function. So this would be 3 minus 4, and then x is -4 plus h squared. Okay, and if we want, we can think of this as x2, y2. Now h here, h is just some variable, right? It's just kind of a dummy variable just sitting there. The point is that we're going to be looking at, eventually what we're going to want to do is look at what happens as h gets really, really tiny, really, really close to 0. Okay? So first let's go ahead and we can rewrite this. So let's multiply out that second part, our y2 here. So let me see, I get 3 minus 4 times, okay, square the first, double the product, square the last. Okay, and this, well, I can rewrite this guy as -4 plus h And then I have 3 minus 64, and minus a minus plus 32h, and then minus 4 minus h squared, so minus 4h squared. Okay, and this, let's rewrite one more time as minus 4 plus h, and then 3 minus 64, that's negative 61, plus 32h minus 4h squared. Okay, again, this is just x2, y2. This is just some point. It looks kind of ugly, and it looks kind of ugly because rather than just two numbers, right, rather than just say negative 4, negative 61, this thing has variables in it, right? But for any given value of h, you just plug it in and you just get two numbers. So now what we're going to do is just like before with lines, we're going to look at change in y over change in x, okay? So our y2 in this case is minus 61 plus 32h minus 4h squared. And then we're going to subtract y1, which was minus 61. So minus a minus 61 over, okay, now x2 is negative 4 plus h. And then x1 was just negative 4. Okay, so this is just y2, y1, x2, x1. Again, if you flip it and you do y1 minus y2 over x1 minus x2, totally fine, you will get the same thing. But this is how I'm writing it. Okay, now we're going to simplify. So the numerator looks really ugly, but notice this. I've got negative 61 and then minus a negative 61. So that's negative 61 plus 61. So the 61s disappear. Similarly, in my denominator, I've got a negative 4 minus a negative 4, so minus 4 plus 4. So those guys cancel out. And this is just 32h minus 4h squared all over, I'm just left with h downstairs. And now I've got h's all around. Two h's there, h squared. And so this just becomes 32 minus 4h. Okay, so now, remember kind of what we said to start when we were setting all this up. We want to know what happens. So what happens to dy dx, or delta y, change in y over change in x? What happens to change in y over change in x as this h gets really, really tiny, right? In other words, as h goes to 0. That's kind of what we want to do. And so this brings us to the calculation. We want the limit as h goes to 0. This is new in this section, this idea of a limit. So the limit as h goes to 0 of delta y over delta x. Well, we just showed that delta y over delta x is just 32 minus 4h. And in this case, since we just have a very nice polynomial here, to find the limit, all that we have to do is, come back, is we just plug in h equals 0, right? We're plugging in this value for h. If this was, say, as h approaches 1, you would just plug in h equals 1. But here we want the limit as h approaches 0. So this becomes 32 minus 4 times 0. And let me get on my calculator. Beep, boop, 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 beep, boop, boop. Let me see, that is just 32. That was a joke. I'm sure that my sound effects were very realistic, but in fact, I did that in my head. Don't worry, maybe someday you can too if you have a bachelor's. That was a joke. Okay. In short, this is the slope that we get. Okay, our slope is 32. So let me walk through the process again, kind of look at the key takeaways from this. So we know how to find the slope when we have a line. That's something that we've been doing, that we've done before. And so what we do to find the slope of the curve is we throw in this dummy variable h. So we add h to the x coordinate, and then we throw it into our function, into our formula, in this case for y. And this gives us another point, right? It looks kind of ugly because we've got h's all around, but it gives us another point. We then use our same change in y over change in x formula, which we've done before. And usually you're going to get some nice simplification like we got here at the end. Finally, we are then interested in the limit as h goes to 0. The reason that we're interested in the limit as h goes to 0 is because then -4 plus h gets really, really close to just -4. And that's the point that we're interested in. So then we take this limit here at the end, and in this case, it's nice and simple. Because it's just a polynomial, we can just plug our value into the expression and we get our solution. Okay, so as I hope you can see, a lot of this is really just taking the same ideas, which we've done previously in mathematics, and applying them in a slightly different context, this time to a curve rather than a straight line. I hope that as you continue throughout mathematics, both in this course and beyond, you'll start to see that a lot of quote, new mathematics that you're going to learn is really just different ways of looking at things that you've done before. And that's what we're doing here. Next up on the docket, so these first two problems were actually recommended by Mackenzie, so shout out to Mackenzie. Problem 5 is going to be similar, but it's always good to practice when we're doing a new skill. Find the slope of the curve. Oh, I should mention, let me write this first. So the second part of problem 4 asks you to, so I'll make a note of it here. We won't go through it, but I'll explain basically what to do. So 4b asks for the tangent line at the point at P. So in this case, I think it was -4, -61. But we have a point. We have a point. Right, our point is just P. And a slope, now we have a slope. Right, we found that slope to be 32. So then you're just going to use the point slope form of a line. Point slope form. And then you're just going to plug it in and simplify if you like. So 4b is very much just use what you've done before. The difference is that here, again, since we don't have an actual line, we have a curve. The slope which we're going to use is going to come from this calculation, which we just did. Okay. 5 is structured the same way in that it also has a second part like that, but we're just going to do the first part again. Y equals x squared minus 2x minus 5 at P equals 2, -5. And this time it says to do it by finding the limit of the secant slopes. But really, so it says to do it by finding the limit of the secant slopes through P. But really, this is what we did the previous problem. We just didn't explicitly say it that way. Okay, so find the slope of this curve through this point. So, like we did before, the secant slope through P. So if you don't remember what a secant slope is, this is saying, well, here we have another parabola. This time it's opening up. So our parabola is something like this. The secant slope is going to be like, if this is P, and this is some other point, I'm going to call it like other point. The secant slope is just the slope of the line through these two. Okay, so that gives us our secant slope. This is a secant line. So then the secant slope is just the slope of that line. So the secant slope through P, Well, just like before, it's going to, so we want, yeah, let me say it this way. The secant slope is going to be given again by change in y over change in x. Okay, so let me, how do I want to, let me write the secant slopes through P, and we'll call our other point 2 plus h, and then, I'm disorganized, hang on a minute. Secant slope through P, and our second point is going to be 2 plus h, and just like before, we're going to plug 2 plus h into our formula. So 2 plus h squared minus 2 times 2 plus h minus 5. Okay, again, this looks kind of ugly, but it's just a point. Okay, well this, the x-coordinate is still just 2 plus h. The y-coordinate is now 4 plus 4h plus h squared minus 4 minus 2h minus 5. I feel like I'm going through some of these algebraic steps a little bit quickly, but I suppose the nice thing about a YouTube video is that you can slow it down and check my work as you need to. So I'm not going to waste a ton of time on these algebraic steps all the time. So then this simplifies to h squared, let's see, plus 4h minus 2h gives me plus 2h. And then I've got 4 minus 4 is 0, minus 5 is just minus 5. Okay, so again, if you like, we can think of this point P as being our x1, y1. And the second point here as x2, y2. Okay, so what we want, I'm going to go ahead and write the limits from the beginning now. We want the limit as h approaches 0 of change in y over change in x. Okay, well, change in y over change in x. So the change in y is going to be y2. So I'll write this out. y2 minus y1 over x2 minus x1. This step is completely unnecessary, the second step, but it might be helpful for you to understand what's going on here. Okay, so y2, we're just going to plug in our values now. That's h squared plus 2h minus 5. So that's y2 minus y1 is negative 5. Okay, so minus negative 5 over, now in our denominator I have x2, which is 2 plus h, and then minus 2. So we get to do some simplifying now. Let's see what's going on here. Numerator, h squared plus 2h, those two guys aren't going anywhere. But then I see I've got minus 5, and then plus 5, this minus and negative 5. So those guys are hashtag canceled. And then by denominator, just as with the previous problem, I have 2 and minus 2. So I just have an h down here. Again, this is going to simplify, limit as h approaches 0 of h plus 2, right? Again, I've got these h's all over the place, so they're canceling. And this guy, this limit is just equal to 2, because again, we can just plug in h equals 0 here. And so that gives me my slope. So this is basically the same procedure as before. Here we started writing limits earlier on, but it doesn't make a difference whether you do the algebra first and then write limit at the end, or if you go with limits the whole way. Now it is important, this is a very important point. If I were to not write limit here and just say that this line here, the green star, is equal to the second line. So if I call this star 1 and star 2, star 1 is not equal to star 2. if I get rid of the limit. No limit with star 2. Okay, that's very important. If I write the limit here, and I say that's equal to something, well, that's if I'm not taking the limit yet, I still need to copy down this limit. That needs to be with every single line. Okay, so you'll notice we write limit, 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 limit. At the end here, we don't write it because at this point, we've already taken that limit. This is whenever we plug in h equals 0, so now it's gone. Perhaps it might be helpful to think about this, and the reason I say this is because that is such a common mistake. And it's especially in this online course in which you're not showing your work as much, it's not going to be as huge a deal. But mathematically speaking, it is very important. So think about it this way. If I just wrote sine of A equals A, clearly that's not always true, right? However, and that's basically the same thing as what we're doing here if we eliminate this limit. Because the limit is basically just some function. And so if I write that these two things are the same, and so if I get rid of that function, right, like down here, if I get rid of sine, that is certainly not the case. It's not always going to be true. That was a big spiel. I'm going to get rid of all this markup in case anybody goes back to look at this later. I don't want to confuse them. But I felt that was worth mentioning. Okay, and again, that's something that I see all the time in Calc 2, so it's a tricky thing to get a handle on. But just make sure that whenever you are taking a limit, you are writing that down so that we know. Okay, enough talk, more problems. Let's jump to problem 15 now. So problem 15. Yes, I want to leave this question. 15. Okay. So this one says to find the limit, and our limit here is limit as x goes to 7 of x squared minus 5x minus 14 over x minus 7. Okay, so before, and I hope that this becomes your intuition for virtually every limit, the first thing that you want to try is just plug in the value. So plug in this case, x equals 7. Just plug it in and see what happens. Before, with our previous two examples, like here, we plugged in h equals 0, and boom, we got our answer. Same thing happened with problem 4. So let's try that here. Let's plug in x equals 7. Well, then this gives me, let me see, 7 squared minus 5 times 7 minus 14 over 7 minus 7. Uh-oh. This is a big uh-oh, because 7 minus 7 is 0. So now I'm dividing by 0. And that is, no, that is bad. And we're sad. We can't just plug in x equals 7 here because whenever we do that, we get something that doesn't make sense. Right? Dividing by 0 doesn't make sense mathematically. So, when that doesn't work, we generally are going to have to do some algebra. Okay? In this case, so we have limit as x approaches 7 of our numerator is x squared minus 5x minus 14 over x minus 7. And let me use this opportunity to kind of emphasize what I was saying before. So we can factor this numerator as x minus 7, x plus 2, over, now I just have x minus 7. This is not true what I've written here. Okay? The factorization is correct. That is a correct factorization of the numerator. And so these two things, the two things I'm going to circle here in yellow, these two things are equal. However, the problem is that just this fraction over here on the right is not equal to this limit. Okay, the limit here is important. So that limit needs to go with us whenever we progress forward. So let me now below this, let me write what I really mean to say, which is that this limit here is equal to the limit as x approaches 7 of x minus 7, x plus 2 over x minus 7. Okay, I hope that is starting to make some sense. Again, I admit in this context in which you're not really doing and submitting handwritten work, it's going to be less of an issue. But I still hope it's something important that you take out of this, because if you continue in mathematics, notational things like that will be very important. So it's good to develop those habits now. All right, so now, what was the advantage of factoring like that? Well, the advantage was that now I can cancel x minus 7, x minus 7. And so this is just the limit as x approaches 7 of x plus 2. And that is just equal to 9 by plugging in x equals 7. Okay. So again, one of the main points of this problem is that the first thing that you should do, which I'm hoping you'll get sick of me saying this by the end of this video, the first thing that you should do anytime you take a limit is just plug in the value and see what happens. A lot of times it won't work out. Like in this case, unfortunately, we didn't get something that made sense. In that case, you generally have to be a little bit clever, do a little bit of algebra. A lot of times it's going to be some factoring, which looks something like what we did here. So we were able to factor. Let me put a big X through this now to make it clear that we did not go that way. Generally, you're going to have to do some sort of factoring to cancel stuff out, and then you get something which does make sense. And so that's what we did here. I think just about every time at the end, you're going to get something that you can just plug in the value. If not every time, certainly most of the time. So that's kind of the goal that you're shooting for. Next, I would like to talk about problem 17. And problem 17 is similar, but a bit trickier. Find the following limit. Okay, so this time we have the limit as u approaches 4 of u cubed minus 64 over u to the 4th minus 256. My goodness, what big numbers you have there. So we want to find this limit. Okay, well, just like before, the first thing I want to do is plug in u equals 4. So u equals 4 gives me 4 cubed minus 64 over 4 to the 4th minus 256. And as everybody knows off the top of their head, 4 to the 4th is 256, right? You all know your fourth powers of the integers, I assume, off the top of your head. That's a joke. I certainly don't know mine. You are not expected to. But anyways, it does turn out that 4 to the 4th is 256, 4 cubed is 64. And so this gives me, again, a 0 in the denominator, which is bad. And we are sad again. So again, we're going to roll up our sleeves. We're going to work ourselves around this. We're not going to give up. We certainly do not give up as mathematicians. And what we notice is that this numerator is a difference of cubes. right? U cubed, that's clearly a cube. It's U cubed. And 64, we just said, is 4 cubed. So we're going to use the difference of cubes formula, which again, I'm sure everybody knows off the top of their heads. And again, that is a joke because I most certainly do not. So this then is a squared plus ab plus b squared. Okay, and if you don't believe me, well, let's multiply this out to check ourselves real quick. So I get a cubed plus a squared b plus ab squared, and then minus a squared b minus ab squared minus b cubed. And yep, sure enough, cancels, right? I've got a plus a squared b, a minus a squared b, and a plus ab squared minus ab squared. So we're just left with a cubed minus b cubed, as we had hoped. That was also a joke, by the way. I don't expect you to necessarily know that off the top of your head. It would be a good thing to know moving forward because I wouldn't be surprised if you were to see a quiz or exam problem which looks something like this. So it would probably be a good thing to keep noted in your memory. In any case, let's go ahead and return to our problem. So now, limit as u approaches 4, well, I can rewrite the numerator. I can factor that numerator as we see here. And in this case, a is u and b is 4. So my numerator is now u minus 4 times u squared plus 4u plus 16. Now my denominator is actually a difference of squares, right? Because u to the 4th is u squared. And 256, as it turns out, equals 16 squared. Okay, you can see this also because this is equal to 4 to the 4th, which is 4 squared squared. And so we should know for sure how to factor things, a difference of perfect squares. So I have u squared minus 16 and u squared plus 16. Okay. So if we try to plug in u equals 4 again, then we are setting ourselves up for failure, unfortunately, because I'm going to get a 0 and this u minus 4 will give me 0. And so will u squared minus 16 if u is equal to 4. So unfortunately, that didn't quite get the job done. I don't see anything that I can really cancel right off the bat either. However, I'm not done factoring because now I have another difference of squares in u squared minus 16. So my numerator I'm going to leave alone. And then I'm going to break up u squared minus 16 as u plus 4, u minus 4. I'm going to leave my u squared plus 16 alone. And now I've got some nice cancellations. My u minus 4, na 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 na, hey, 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 goodbye. And let me see, so now my numerator is u squared plus 4u plus 16. And my denominator is u plus 4, u squared plus 16. And this is something which we can plug u equals 4 into. Plug in u equals 4. I'm not going to go through it here. You can do that. It's just a little bit of computation, which you are totally capable of doing. So I'll just circle that, plug in u equals 4. Whatever you come out with, that will be your solution. Okay? So again, this one worked quite similar to the previous one. We tried to just plug our value in here to get started, but that didn't get the job done, and we cried a little bit. But we picked ourselves back up, and we noticed that we could factor things. We had a difference of cubes in the numerator and a difference of squares in the denominator. We plugged in u equals 4, and again, we came up short. after our first factorization. But thankfully we weren't done yet, and we could do a bit more factorizing to get us where we wanted to go. Okay, so sometimes it will take a little bit longer. It'll take a few more steps. But in any case, doing algebra like that usually will help you whenever you are stuck. Okay, next is problem 18. And for 18, we are again going to find a limit. So find, in this case, we have, I would say this limit probably has a face that only a mother could love. I'm sorry, limit, but you know it's true. Boom, boom, boom. So the limit as x approaches 196 of the square root of x minus 14 over x minus 196. So, you know what I'm going to say first. Let's just plug that bad boy in. First, plug in x equals 196. Okay. Well, this gives me root 196 minus 14 over 196 minus 196. Okay, well, my denominator I can see is 0. It turns out actually that my numerator is also 0. And so this, unfortunately, we're dividing by 0 again. So this is no bueno. Okay. And that means that we're going to have to be a bit more creative. Now here, the last couple of times we were able to do some very nice factorizing, but I don't see anything that we can factor here. Like I don't see any squares or cubes or anything that we can break down. So what we're going to do is we're going to use a fancy trick called rationalizing the numerator, and it goes a little something like this. So we're going to multiply by the conjugate of the numerator over the conjugate of the numerator. In other words, we're just going to multiply by a big fat 1. But in doing so, we're going to get some nice things are going to fall out nicely algebraically. Now, what is the conjugate? I hope that that's something which you remember or you've seen. I imagine that you saw it in the textbook or in Mackenzie's video. But if not, the conjugate, so if I have a plus b, then the conjugate becomes a minus b. So all that we do is we just flip the middle sign. Flip the middle sign. Right, I go from a plus b to a minus b. So in this case, let's look at what we're doing. So we're looking at the limit as x goes to 196 of, let's see, we had root x minus 14 over x minus 196, and we are multiplying this by, okay, so the conjugate of our numerator here. So the conjugate is going to be root x plus 14. Okay, again, we're just going to flip this sign. So root x plus 14 over root x plus 14. Now I promised you some nice algebraic properties. Well, here they come, I promise. So let's see what happens whenever we multiply this out. X approaches 196. Okay, my numerator, I see I have root x times root x. That just gives me x. Root x plus times positive 14, so plus 14 root x. And then minus 14 root x. And then minus 14 times 14, so that's minus 196. Yeah, because it's minus 14 times 14. Okay. And now my denominator, I'm just going to leave it actually. My denominator I'm not going to multiply out. Let's just leave it like this. Because now, watch what happens. Get ready for your mind to be blown. Well, the numerator here is just x minus 196. And then x minus 1, I've got an x minus 196 up here, and an x minus 196 down here. So this is just the limit as x approaches 196 of 1 over root x plus 14. And now we can just plug in our value of x. Plug in x equals 196. And I get 1 over root 196 is 14. And 1 over 28 gives us our answer. Okay. So this time, we again had something that plugging in our value for x right away did not get the job done. We couldn't factor, so this was different from before, and we used this neat trick called rationalizing the denominator. Or excuse me, rationalizing the numerator. And by that we mean multiply by the conjugate of the numerator over the conjugate of the numerator. So multiply by 1, or remember the conjugate just means flip the sign in the middle of the two things. This is called rationalizing because what happens is what these square roots are going to cancel out. That's not an accident. That is supposed to happen. That's the point of rationalizing the numerator. We get rid of those square roots. And then here we have something which we could cancel out nicely. And then we just plug in our value, as always, at the end. Okay? Okay, wonderful. I love that one. That's such a cute one. Ugh, I love that one so much. Okay. Let us jump to 21 now. 2 more problems on the docket for today. 21. Excuse me. Okay. Oh, so 21, we're going to start looking at some of these limit laws that we mentioned at the beginning. So suppose that the limit as x approaches 2 of f of x equals 6, and the limit as x approaches 2 of g of x is negative 3. Then we are going to find some more limits. Find the following limits. Okay, so notice here, we're not actually told what the heck f and g are. We don't know what these functions are. All that we know is their limit at this one particular value. In particular, the limit as x approaches to 2. It is also important to notice that both of these are the same x value. The limit as x approaches 2. And you'll notice as we go throughout there are 4 computations we're going to do here. As we go throughout this, all 4 limits which we're going to compute are going to involve limits as x approaches 2. We know absolutely nothing about the limit as x approaches any other point. Okay? All that we know is information about what happens near 2. Okay, if this said, for example, if this said the limit as x, actually let me just do this. The limit as x approaches 23, we would have no idea. Because I have no idea what f and g are doing around 23. Okay, so just keep that in mind. What we're going to do here, all of these are going to be at the same x value, which is important. The first value which we are told to compute is the limit as x approaches 2 of the product f of x, g of x. Now limits are very nice in that what we can do is we can distribute the limit basically to write the limit as x approaches 2 of f of x times the limit as x approaches 2 of g of x. Okay, so like I said, we're basically just distributing this limit here and here. We know these two values. These two values are given to us. The limit as x approaches 2 of f of x, that's 6. And the limit as x approaches 2 of g of x is negative 3. And so this just becomes minus 18. Now, a word of caution, and I'm going to make a few remarks like this over the course of this problem. It is not true, for example, that sine of A times B is not the same as sine of A sine of B. So right, we all know that's true. So what is the point that I'm trying to make here? Well, the point that I'm trying to make is that with limits, we do have this very nice behavior where we can just break up this limit, right? We can look at it at each of these two pieces. But that's not true with every function. That is not true, for example, with the sine function. I cannot just distribute the sine to the A and to the B. Okay? So this is a very special thing about limits, which makes limits very nice to work with. So keep that in mind as we move forward, that these algebraic rules are very simple and work just like you would hope they would. But this is very special to limits and is not true of functions in general. Limits are very special. So good job, limits. As I said before, as I hope you will take away from this video, limits are quite lit. Anyways, next up, limit as x approaches 2 of 2f of x, g of x. Okay. Well, another nice thing about limits is that whenever I have a constant, I can pull that constant out front. Okay, so here 2 is a constant, so it comes out front. F of x, g of x. And so the limit as x approaches 2 of 2f of x, g of x, well, that's the same as if I brought that 2 out front and wrote it as 2 times that limit of f of x, g of x. Now this second limit, or this limit here of f of x, g of x, we just showed in part A that this was negative 18. And so this limit comes out to 2 times negative 18, or as most people write it, negative 36. Okay? Now let me again step aside and highlight that sine of 2a is not the same as 2 sine of a. Right? There are some special cases where this is true. For example, if a is equal to 0. And the same is true in the first part with this earlier example with sine. If a and b are both equal to 0, then sure, that does work out. But in general, this is not always going to be the case. I cannot just pull that 2 out front of the sine. I'm picking sine here just because it's a function which we're all familiar with. However, the point is that this is just not going to be true in general, okay, with any function. However, limits are nice, and they allow us these very nice properties. Let's go to part C now. In part C, I want the limit as x approaches 2 of, in this case, f of x plus 4g of x. Okay, so that's what we want. Well, another nice limit law is that I can rewrite this as the limit as x approaches 2 of f of x plus the limit as x approaches 2 of 4g of x. Okay, so now we saw in part A, we distributed the limit kind of throughout this multiplication. And here we're demonstrating, or using the fact rather, that I can distribute this limit across addition. You can do it there and there. Okay. Well, and as we said just a moment ago, I can pull this 4 out front of the second part, give me 4 times the limit as x approaches to g of x, which means that this comes out to, well, this first limit, that's just 6. We're given that. And then I have 4 times the second limit, which we know is -3. So let's see, it's going to be 6 plus -12. And that, I'm pretty sure, is -6. You know where I'm going with this. Is it true that sine of a plus b equals sine of a plus sine of b? Absolutely not. So again, this is something special about limits, which we love. Limits, you guys are indeed lit. Certified lit. AP lit. And finally, let us do part D of this problem. Part D says, let's look at the limit as x approaches 2 of, got a fraction here, f of x over f of x minus g of x. All right, so this is the limit that I am interested in now. Well, it is indeed true, as you would hope and as you might expect, that I can break this up and look at and distribute the limit to both the numerator and the denominator. Limit as x approaches 2. Notice again, kind of like I talked a little bit earlier about notation, but notice that every single time, not only am I writing limit, but we're writing the limit as x approaches 2. Okay, that's important as well, that we are clear about where we are interested in this limit. Well, now my denominator, just as we did with addition, we can distribute this limit to each function. G of x. And this, my friends, comes out to, okay, well, the numerator is 6. The denominator is now 6 minus a -3. So that gives me 6 over 9, or 2/3. And yes, sir, it is indeed true that sine of a over b is not necessarily sine of a over sine of b. So we cannot simply distribute most functions like that. However, when it comes to taking limits, things work out so nicely, you couldn't really ask for anything better. Okay, so keep this in mind whenever we are dealing with limits and other functions. Other functions aren't always going to be as friendly or as lit. Okay, so basically the point here of part C is that, of this problem, problem 21, is that limits behave exactly as you would like and hope them to in terms of algebraic operations. Okay, so we can thank the mathematical gods for that one. Or single god if you're a mathematical monotheist. I don't know your mathematical religious beliefs, and I don't want to assume any. Okay, problem 22. Enough talking, Bailey. You're blabbering on here. Let's get to 22. 22 says if root 5 minus 3x squared is less than or equal to f of x, and that in turn is less than or equal to root 5 minus x squared, for all x between -1 and 1, we want to find the limit as x approaches 0 of f of x. Now, if you're like me, when you read this, the first thing you think is, what the heck? How am I supposed to find the limit as x approaches 0 of f of x if I don't know what f of x is? All that I know that it lives between these two things, but I don't know exactly what it is, so how the heck am I supposed to decide that? Well, notice that if I take the limit as x approaches 0 of this left-hand function, 5 minus 3x squared, well, this is just going to be root 5 just by plugging in x equals 0, right? Because that just becomes 5 minus 0. Similarly, if I look at the limit as x approaches 0 of the upper bound function, so this root 5 minus x squared, well, that is also just root 5 for the same reasoning. Now, I know that at x equals 0, f of x is strictly between these two things. So now, by Sandwich Theorem, one of the most fantastically named theorems in mathematics, by the Sandwich Theorem, the limit as x approaches 0 of root 5 minus 3x squared is less than or equal to the limit as x approaches 0 of f of x, which is less than or equal to the limit as x approaches 0 of root 5 minus x squared. Well, this left-hand limit, that's just root 5, less than or equal to limit x approaches 0, f of x is less than or equal to root 5. So limit as x approaches 0 of f of x is both less than or equal to root 5 and greater than or equal to root 5, which means that it must be exactly equal to root 5. Okay, so this was a very nice application of the Sandwich Theorem, pretty straightforward. Once you know to use the Sandwich Theorem, it's very doable. The important part really is recognizing, oh, this is a situation where I can use the Sandwich Theorem, where it might be useful. The other point that I want to make is that it is important to note that 0 lives between -1 and 1, so it is in this interval here. It is in this interval over which I know this inequality at the top is satisfied. If this asks for, say, the limit as x approaches 2 of f of x, I would have no idea, because I don't know what f of x is doing around 2. All that I know is that it's between these two functions over this specific interval. So within that interval, I am able to deduce some information about the limit. Okay, I think that is all for this video. I certainly hope that you could hear me. I'm sorry for those technical issues. And I, again, appreciate you being patient and understanding as we work through those. Have a great weekend. I will see you next week in our next video. And as always, let me know how I can help you be successful in this class. So thanks, guys.